First, we want to talk about molecules featuring atoms that violate the octet rule by having unfilled valences. All right, so we want to look at situations where atoms have less than 8 electrons. So one of the canonical cases is beryllium. So beryllium tends to only have 4 electrons in molecules. If we look at, for example, beryllium difluoride or beryllium 2 fluoride, beryllium is in column 2A in the periodic table, so it only has 2 valence electrons. Fluorine has 7, so there's a total of 16 valence electrons in this molecule. If we follow our protocols, beryllium is first, so it goes in the middle. We draw the bonds out to fluorine. That is 4 electrons that we've put in those bonds, so there are 12 left. We're going to start by doing lone pairs on the outer atoms to fill to the octet. Fluorine gets the 6 on each. That's 12 electrons, and there are none left. So all of the electrons, as it's written, all the electrons are in this molecule, are drawn on the Lewis structure. We can't add any more dots. We can only move things around. And so we've seen previously that we could maybe make double bonds. So the beryllium, initially it only has the 2 lone pair, single bonds, so it's 4 electrons. It could go to 2 double bonds. We could also get exotic and try maybe a single bond and a triple bond, something like that. And so the structures on the right are preferable potentially because the beryllium atom has an octet of electrons, whereas on the left we would say that's bad because the beryllium doesn't. But if we go through and calculate out formal charges, we can see that in the Lewis structure where the beryllium has the double and triple bonding, that beryllium atom has a formal charge of -2, and the fluorines have a formal charge of +1. In the triple bond situation, the single bonded fluorine does have a formal charge of 0. The beryllium, once again, has a formal charge of -2, and then the fluorine that's triple bonded has a formal charge of +2. Those are really big formal charges, right? We want our formal charges to be as close to 0 as possible for our major structure. Not only that, but in this case, as we are putting positive formal charge on fluorine atoms. And fluorine is the most electronegative atom that there is. It really does not want to have positive formal charges. If we look at this original structure where the beryllium only has the 2 single bonds, everything does have a formal charge of 0. This ends up being the most stable structure for this molecule because the beryllium doesn't fill the octet rule, sure, but the formal charge is only 0, and beryllium, it maybe wants to follow the octet rule, but fluorine really doesn't want to lose any of those electrons, and fluorine is going to be able to more strongly overcome any sort of resistance that the beryllium has and hold on to those electrons, and beryllium has just the 4 electrons. So when we look at this, it is generally the case that when beryllium forms molecules, it only has 2 bonds. It forms 2 single bonds, and its total valence is 4 electrons. Boron is a similar case. Boron has in its valence, when it's in molecules, 6 total electrons across 3 bonds. So BF3 follows the same idea. The boron atom does not have a full valence. But importantly, in these Lewis structures, all atoms have a formal charge of 0. And remember, the purpose of Lewis structures is to reflect what the molecule really is. We know that the boron is bonded to 3 fluorine atoms, and they're pretty long bonds. They're the characteristic of single bonding. Same thing with beryllium. They're relatively long single bonds. It is experimentally, we have evidence to suggest that there's not double or triple bonding that's present. And we have theoretical ideas as to why that probably doesn't happen because fluorine is really electronegative. We can also understand the mechanism if we look at, say, the Lewis dot structures of beryllium and boron. We can understand the formation of bonds as pairing up those unpaired electrons. Well, beryllium only has 2 valence electrons and boron only has 3. And when you form a covalent bond, when you're sharing electrons, the atom has to donate 1 electron into that pair. So beryllium only has 2 electrons to share. It can only form 2 bonds. Boron only has 3 to share. It can only form 3 bonds. in order to get some sort of double bonding or triple bonding in one of these cases, those electrons would have to be fully donated by, say, the fluorine. Say these 2 electrons would have to go from being on the fluorine to being paired up. And we know that is something that fluorine does not want to do. Fluorine's extremely electronegative. It wants to hold on to all of its electrons. It does not want to share them. That's not to say that these boron atoms and beryllium atoms are like stable or that they are satisfied, right? Atoms in general want a full valence. And in the case, these atoms just can't get that valence from the atoms they're currently bonded to. But if there's another molecule that's present that, say, features other types of atoms or electrons in a slightly different situation, you could maybe get some bonding. What we call this type of bonding is a coordinate covalent bond. So covalent still means that there is, sharing of electrons. But in this case, we're using this word coordinate, where this is corresponding to basically one atom that's coordinating with another is kind of what the language is going on here. And what happens here is the idea of what we talked about, that something that's a lone pair that was previously on only one atom is being converted to a shared pair of electrons. And so what happens is that you have some sort of, say, donation of 2 electrons to be shared between 2 atoms. And so this is how boron atoms in these molecules or beryllium atoms in these molecules can gain an octet, is through this coordinate covalent bond. They have to find some other molecule with a lone pair that's willing to share. So a nitrogen atom in, say, ammonia, it has this nice lone pair right here. And so what it can do is it can share that bond, share those electrons with, say, a boron atom. And then the boron forms this right here would be the coordinate covalent bond. You will note there are charges that are marked on this kind of molecule that has formed. The nitrogen has become positive and the boron has become negative. Those are the formal charges that we're showing here. And you can see that the nitrogen, because it's donating, it's losing, it goes positive and the boron goes negative. Coordinate covalent bonds don't tend to be that strong because, again, nitrogen's pretty electronegative and you're putting a positive formal charge on it. That tends to not be the most stable. So this can form, these sorts of molecules can form. They just, again, it's not really the best case. The atoms that tend to have lone pairs also tend to be pretty electronegative. And so as a result, this is why these borons, can't always find, kind of a good situation as a way to get these extra electrons to satisfy that full octet. But they certainly will form a bond if, say, ammonia is present. If they're in a mixture, they will react to form this new compound. You could see this even in, for example, solid beryllium difluoride. So if you had this case, we know that beryllium wants, say, electrons from somewhere else. Well, if it's solid beryllium difluoride, there's a bunch of other molecules, and those fluorines potentially have those lone pairs. And so you could say, set it up that this beryllium needs 2 bonds, right, to get 4 more electrons towards an octet. And so if you make 2 coordinate covalent bonds, all of a sudden there's 8 total electrons. And this continues on for all of these molecules. And so the actual structure of beryllium 2 fluoride is these gray dots right here are the beryllium atoms. And you can see they have 4 coordinate bonds basically that have formed. And so you can see they are 1, 2, 3, 4 right there. And so there's these ideas that when there's other molecules present, you can start to react with those other molecules. So yes, BEF2 is stable and a single molecule looks just like this. The single molecule looks just like this, but when you start to expose it or allow it to interact with other molecules, you can start to get some kind of fancy chemistry that's going on where you can see changes and you can see things going on where there's interactions between molecules to account for that violation of the octet rule. Try to get back to a full 8. That full valence is desirable. Okay, no questions for participation 626 here. We are now halfway through this set of videos. So if we find any questions in this back half, see you there.